Digitally sketching is a fast and natural way for artists to form the foundations of their drawings. However, the sketch lines need to be consolidated to form a final image as the artist intended. Hello, my name is Brendan Bickford, and today I will discuss a paper that uses a novel approach to solve this problem. The paper is titled StrokeAggregator, Consolidating Raw Sketches into Artist-Intended Curve Drawings. Before a sketch can be used for shading or for modeling, it must first be cleaned up. In this example, it took an artist nearly 30 minutes to consolidate the sketched lines in this drawing. So what if this process could be automated? Here are some examples of previous attempts to automate this process. As you can see, the results are fairly good, however, none of them quite compare to the results from an artist until now. This model uses perception-driven parameter setting. The previous papers require pre-processing of the sketch or fine-tuning of the parameters to get a good result, but this method requires neither. The perception-driven parameters are based on feedback from participants in surveys. For determining a narrowness factor, they found that as a rectangle gets wider, it was perceived as being thinner. And for a proximity factor, they found that participants naturally grouped lines that appeared relatively close together. Using this insight, they formed a new aggregation algorithm. The algorithm begins by forming coarse clusters. These clusters are formed conservatively based on the angular compatibility and local proximity of the strokes. So any lines that are connected or appear parallel to each other are clustered together. These coarse clusters are then separated in a refinement stage. Even if the strokes are connected, the algorithm will evaluate the internal unevenness of the strokes to detect any possible branches. The coarse cluster is then split into subclusters at each of these branches. As you can see in this example, the coarse cluster A is split into 3 parts, and the coarse cluster C is split into 2 parts. After the refinement stage, the clusters have been split into their smallest component parts. In order to combine them back into their optimal aggregate curves, the algorithm uses a unification stage. In this stage, every pair of clusters is evaluated once again for angular compatibility and local proximity to each other, this time using a tighter threshold. If the pair is within the threshold, they can then be merged together into a single cluster. This process will repeat until no more clusters can be merged. Finally, a polyline is fit to each of these unified clusters. To do this, each of the strokes is reordered from left to right, then the aggregate curve is calculated using a modified moving least squares algorithm. In order to determine the thickness of the line, they use a strength in numbers approach. Essentially, this means the more strokes there are in a section, the thicker the line will be. When evaluating this process, participants rated the algorithm's results on par with the artist's results 50% of the time, and they even preferred the algorithm's results 25% of the time. When comparing this with methods from previous papers, the participants preferred these new results 80% of the time. Take a look at the results for yourself. Overall, this paper outlines a robust stroke aggregation process that can be used by artists to save time when cleaning up their drawings. Thank you very much for watching.